Hey guys, we today are going to talk about two topics. We're going to talk about limits at infinity. So this means what happens if you look at a limit as, say, x goes to infinity, positive or negative. And then also we're going to look at what's called L'Hopital's rule, which you guys may have heard of before, but this is actually going to be a new topic for y'all. And it allows us to use the derivative, just we're going to do really simple derivatives to evaluate limits. It's a really neat rule. So let's talk first about limits at infinity. So limits, most y'all have actually learned about limits at infinity before you reached calculus because you talk about them in pre-calculus because limits at infinity are really just horizontal asymptotes. So we're interested in a horizontal asymptote. We're interested in what happens to y as x goes to infinity, which is exactly what we're going to look at if we look at a limit at infinity. So let's take a look at this example. So say we had the limit as x goes to infinity of 3x squared minus 4x plus 1 all over x squared minus 3. So if we're really looking as x goes to infinity, what happens to y, or f of x, as we might call this, you guys probably know a rule that you learned, hopefully you know, in pre-cal that tells you, you compare the degrees of the numerator and denominator. Degree is, your highest power, and then you have a certain rule if they're equal, if the top is bigger than the bottom, or if the bottom's bigger than the top. Um, my kids before have told me this crazy acronym, and they would always say it. I think it's Boba Boughton Eats DC. I could not tell you what those things stand for, and I'm not a big fan of those acronyms. But here are the rules. So let's say your degree of the top is n, and the degree of the bottom is m. Then here's what happens. If n is greater than m, the degree of the top is greater than the degree of the bottom, then you have no horizontal asymptote. So what's going to happen is that x goes to infinity, y is just going to go to infinity. It's not going to approach a single value. The next one is if n is less than m. So if the degree of the top is smaller than the degree of the bottom, then it's going to go to 0. Then you have a horizontal asymptote at y, or f of x, is equal to 0. And then the interesting thing comes whenever they're equal to each other. Your horizontal asymptote at the ratio of the leading coefficients, which is just the number in, oh, let me write this first. So that's just going to be the two numbers, so two constants in front of your x that has your degree, your x to the highest power, and then you're just going to make a ratio out of those, the top over the bottom. I'm not a big fan of memorizing rules like this. I would much rather you guys understand where they come from. So I'm going to show you how I solve limits at infinity when it's a polynomial over a polynomial, or other cases like exponentials and stuff, where you don't really have to just go through and memorize the rules, and it basically proves all of these for you. So let's go back up to this example that I showed you. Oh, sorry. I guess that's close enough. Okay, there we go, sorry. And then I lost my limit, but I can put it back. The limit as x goes to infinity. All right, so if you think about the rule I just told you, the degree of the numerator and the denominator are equal to each other. So we could just use the rule and say, okay, it's the ratio of the leading coefficients, which is going to be 3, right, over 1, and so your limit's going to be 1. But what you really want to do, the idea basically, is to get the infinity out of the denominator. And so, how we can do this algebraically, which is pretty neat, is we can. I'm trying to get rid of these squares. Sorry. Oh, there we go. Is we can take and we can look at the highest power of the denominator, which for us is going to be x squared, and then we want to divide both the top and the bottom of our fraction by x raised to the degree of the bottom. So in this case, I look at my bottom, my degree is 2, so I'm going to divide the top and the bottom by x raised to that power. And basically, the only thing that you have to know is what happens to like 1 over x squared, 1 over x cubed as x goes to infinity. So I'm sure you guys know that if you take and you let your denominator go to infinity and your top remains constant, then the whole thing's going to go to 0 because you're going to have a super big denominator and then, a constant or a tiny numerator, and that's basically 0, 1 over 10,000, 1 over a million, and so forth. It's going to go to 0. So what I'm going to do here is I'm going to distribute this 1 over x squared to everything in my numerator and denominator. So then it'll become the limit as x goes to infinity of 3x squared over x squared. So that's just going to be 3 minus 4x over x squared plus 1 over x squared divided by x squared over x squared minus 3 over x squared. And then I'm going to do a little bit of simplifying, and I'm just going to cancel the x's. And then I end up with the limit as x goes to infinity of 3. Pull this up so I can see what's going on. Minus 4 over x plus 1 over x squared all over 1 minus 3 over x squared. And then you guys know by your limit laws that as long as the denominator is not 0, that we can just basically distribute this limit to each piece of our numerator and our denominator. So I'm going to just kind of quickly show you what happens. So if I look at the limit as x goes to infinity of 4 over x, then, my denominator is going to get super big, my numerator stays constant, so that's just going to go to 0. The same thing with 1 over x squared. That's going to go to 0. And the same thing with 3 over x squared. That's also going to go to 0. And then I'm left with 3 minus 0 over 1 minus 0, plus 0, sorry, which is just 3 over 1, which is 3. And so this is going to hold true for any polynomial over any other polynomial. And every time you do it, depending on what degree you have in top and the bottom, you're going to get the same result as you would have if you would have used that horizontal asymptote rule. So remember, the idea is that you look at the degree of your denominator, which is in green right here, and then you take that and you divide both the top and the bottom by 1 over x to that degree. And then if the degree on the top is higher, then you'll be left with an x in the numerator, and then that'll obviously go to infinity. If the degree of the bottom is higher, you'll end up with 0 in your numerator, and then a constant in your denominator, and that whole thing will go to 0. So let's look at a couple that would be a little trickier than that. So let's look at the limit as x goes to infinity of, say, 3x cubed minus 4x all over the square root of 4x to the fourth minus 2x. Yeah, that sounds good, minus 2x. So if you look at the bottom, I told you to look at the degree of the bottom. Well, we have x to the fourth, but that's not really your degree because you're taking the square root of it. So although you and I know that I can't really distribute this square root to both terms, what happens to my degree is that I would actually take the square root of x to the fourth, and that would give me my degree. So the degree of my denominator is actually equal to, x to the fourth to the 1/2 power. So it's going to be 2. So now I want to take, and I have the degree of my denominator, which is 2. So I'm going to, just like I said before, divide the top and the bottom by 1 over x, or sorry, multiply the top and the bottom by 1 over x raised to that degree. Now, I can't really distribute that 1 over x squared into my denominator in the form that it's in, but I can manipulate the form so that I can distribute it in. And let me show you how that's going to work. I'll go ahead and clean up the numerator a little bit, and I'm going to skip a step that I did before. So I'm going to say that 3x cubed all over x squared is just going to be 3x, right? Because the x's will cancel. And then 4x over x squared is going to be 4 all over x. And then in order to distribute the bottom, I'm going to rewrite this as 1 over the square root of x to the fourth, because that's equivalent to 1 over x squared. And so now that I have a root in there, I can have that as a root. I can distribute it in to my roots, and let's see what I end up with. When that as x goes to infinity, 3x minus 4 over x all over. And then now when I distribute it in, the x to the fourths are going to cancel, and I end up with the square root of 4 minus. And then when I distribute that in, the x and the x to the fourth, I'm going to cancel one of those x's, so I end up with 2 over x cubed. And now I'll look and see what's going to go to 0. And so anything with the x in the denominator is going to go to 0. So both of those are going to go to 0. And I'm left with basically 3x over the square root of 4. And since I have an x in my numerator, that x is going to go to infinity, and the bottom is constant, so this is going to equal infinity. So if we think about that horizontal asymptote rule that I showed you before, here the degree of my top is 3, and the degree of my denominator is actually 2. We determined that. So the degree of the top is higher than the degree of the bottom, so the whole thing is going to go to infinity. Another cool trick you can do is with exponentials. And in fact, you can use the same method if you have like exponential expressions, but you can't use your horizontal asymptote rules. And one of the big ideas with limits at infinity is that you want to see which is going to go to infinity faster, your numerator or your denominator. And in the case where the degree of the numerator is higher, the numerator is going to go to infinity much faster than the denominator, which is going to make the whole thing go to infinity. If your degree of your denominator is higher than the degree of the numerator, the denominator is going to go to infinity much faster than the numerator, which is going to make the whole thing go to 0. And then if they're equal degrees, they're going to go to infinity at the same rate, which means that you're just going to end up with the ratio of your coefficients. And so we can kind of apply that idea to an example that looks like this. Um, so here we have exponential expressions. And so I once again take and I look at the denominator, and I don't look at the degree of the denominator, but I look at that exponential. And so I have a 4 to the x as kind of my, exponential term in the bottom. And so I want to take and divide the numerator and the denominator by that exponential expression. So I'm going to divide the numerator by 1 over 4, multiply, I guess, by 1 over 4 to the x, and then do the same thing to the denominator, of course. So I still have an equivalent expression. And then I'm going to go through and I'm going to simplify. So the limit as x goes to infinity, this is now going to be 3/4 all to the x if I simplify the numerator, plus 1 over 4 to the x, all over 4 to the x over 4 to the x is going to be 1, plus 2 over 4 to the x. And let's see what's going to go to 0. Let's see. 1 over 4 to the x is obviously going to go to 0. 4 to the x is going to go to infinity at a much faster rate than a constant. And then the same thing goes with 2 over 4 to the x. And so now I'm basically left with 3/4 to the x power. And now you want to use the same property. You want to think which is going to go to infinity faster, if I multiply a bunch of 3's together or if I multiply a bunch of 4's together. Well, obviously the 4's are going to go to infinity much faster than the 3's. Or you could also think to yourself, if I when I raise something to the x power, I'm basically just multiplying it by itself a whole bunch of times. If you take a number less than 1 and you multiply it by itself a bunch of times, you're still going to get a number that's less than 1. And then the more you do it, the smaller the number is going to become. So this whole thing is going to go to 0. Also think about that same concept. 4 to the x will go to the infinity faster than 3 to the x. So this is a really neat trick that you can use instead of having to memorize those horizontal asymptote rules for limits at infinity. Another thing that you can do for limits at infinity is what's called L'Hopital's rule. So let's talk about that for just a second. L'Hopital's rule is a really, really neat rule, and later on in the class, we are going to talk about the proof of it. I don't think that we have the necessary prerequisites in order to, analyze the proof. But it kind of deals with these indeterminate forms of limits. And we have two that apply to L'Hopital's rule. So these are the two that we're going to use. The first one is 0 over 0, and then the next one is infinity over infinity. Now 0 over 0, you would think that would imply that the limit's 0, but that's not necessarily true. The same deal with infinity over infinity. Just like we saw, all of basically the polynomials that we just looked at, if we were to just kind of evaluate the top and the bottom separately, then you would get infinity on the top and infinity on the bottom. And as you can see, those do different things. They don't cancel out and get 1. They don't unless they're going at the same pace. And so you have to be careful when you have these indeterminate forms as to what's going to happen with the limit. There are also several other forms for L'Hopital's rule that we're going to discuss those later. The algebra behind evaluating them is a little tricky, and so we're not going to get into those in this chapter. I just wanted some really basic derivatives for y'all, and not anything that was super complicated since we hadn't covered derivatives yet. So let's take a look. Oh, well, I guess I'll give you the rule. So if you have one of these two forms, so if your form of your limit is, and I'll just say for us at this point 0 over 0 or infinity over infinity, then if you have the limit as x goes to infinity of f of x over g of x, then this is going to be equal to the limit as x goes to infinity of f prime of x over g prime of x. Now, one important thing, and that my students sometimes will make mistakes on, is they'll think, when I have this form and I want to take the derivative, that I'm going to use the quotient rule, which is not true at all. We evaluate the derivatives of the numerator and denominator separately. So, going to write this down because it's really important. So let's take a look at an example. So we could honestly take one of the examples we worked earlier and see if, for one thing, L'Hopital's rule applies. Every time you want to use L'Hopital's rule, it would be required from me, and I believe also the AP exam, that you check the form. And I'll kind of show you my method of how I check the form. But if you don't check the form, 0 over infinity is not a form of L'Hopital's rule. Infinity over 0 is also not a form of L'Hopital's rule. So the only two we're going to use right now are 0 over 0 and then infinity over infinity. So pay close attention. All right, so let's look at this example that we did earlier. There we go. Okay, so if I am evaluating, if I look at each separately and I see what happens, the numerator is a polynomial. So as x goes to infinity, this thing is going to go to infinity. And then in the bottom, it's also a polynomial. So as x goes to infinity, the whole thing's going to go to infinity. So usually I'll just take my limit, I'll draw an arrow because I don't want to put an equal sign because that's not super accurate. And I'll just, write my form, and if it works for L'Hopital's, I'll put a check. So then, to kind of show that I'm applying L'Hopital's, I will put an equal sign, and then I'll just put an L apostrophe H. And then now I'm actually going to take the derivative of the top and the bottom. And I don't really expect you guys to be able to do much more than take the derivative of a polynomial. Just use your power rule. So here this is going to become 6x minus 4 all over 2x. Now if you notice, I haven't actually gotten it into a form where I can evaluate the limit. It's still my form, my form still is infinity over infinity, right? Um, but you can apply L'Hopital's rule as many times as you need to. So I'm going to apply it again. I mean, as long as you still, once you apply the derivative of the top and the bottom, as long as you still have a form of L'Hopital's rule, 0 over 0, infinity over infinity, then you can still use it. So since my form, is infinity over infinity again, I'm going to apply it again. And I get the limit as x goes to infinity of 6 over 2, right? Which is 3. And I've, arrived at the same answer that I got before. And basically, with any polynomial over another polynomial, instead of using those horizontal asymptote rules, another way to do it would just be to, apply L'Hopital's rule a bunch of times. If the degree of the top is higher than the degree of the bottom, you'll end up with just an x, once you take as many derivatives as you need, which would go to infinity. If the degree of the bottom is bigger than the degree of the top, then you'll end up with like 1 over x to some power, and then that will go to 0, which is what the horizontal asymptote rule tells us. All right, so I hope you guys have learned a little bit about limits at infinity and L'Hopital's rule, and I will see y'all later.